Today we're in the Accuray headquarters. It's the manufacturing center. It is in Madison, Wisconsin, and we're in bunker number 2. My name's MACKIE. I was the co-founder of tomotherapy and one of the inventors of the technology when I was a professor at the University of Wisconsin Department of Medical Physics. Well, I'm a medical physicist, so I got a degree in physics, but practiced the physics involved in medicine, and so the fields are radiation oncology, radiology, and nuclear medicine are the ones that I've been involved with for my career. Yeah, so when I was at the University of Wisconsin, a professor of medical physics, I came up with an idea for a better treatment planning system, and with some colleagues there, developed one of the first 3D radiation therapy treatment planning systems, and we spun that into a company that's now owned by Philips Medical. With the proceeds of that, we started tomotherapy in 1997. Right. Today, I have founded several companies. So a fluorescent guided surgery company specializing in vascular surgery and hopefully in the future cancer. It's called OnLoom. I have a veterinary CT scanner company called ASTO-CT that has invented the first scanner that can scan horses when they're standing. And a company called HealthMine, which is a healthcare IT company mining data to help us better understand the phenotype of cancer. So digital health really has the opportunity, if we use digital records, it helps us on a day-to-day basis to track the patients, but it can also be used as a source of data mining. So in other words, we can use that to determine a better description of disease, even the taxonomy of disease, in other words, how to classify diseases based on their phenotype. So in other words, a medical record should be a description both of the phenotype, in other words, the description of disease, as well as the genotype. Putting all of that together, one could get a better idea of the description of the disease, a prognosis of the disease of a particular patient as compared to a cohort of patients, and as well something about how we should treat the patient, or what should be the prescription that we would deliver to the patient, or the drugs that we would give to the patient, or even the lifestyle that the patient should adopt in order to stay healthy. So daily implementation really requires us having a curated set of records for a very large number of patients, so that what we can do is identify what makes a cohort of patients similar, and what that cohort should do in order to stay healthy. I think we're within 5 or 10 years of really being able to learn from the digital record and apply it for all patients. Why do I do what I do today? Well, I mean, I have two choices. I'm retired. I'm an emeritus professor at the University of Wisconsin. I could stay home and watch television, or I could continue to use my brain, and I would rather use my brain than watch television. So that's why I do it today. I do it because I love what I do, and I can't see myself ever quitting. So I was inspired by a Swedish medical physicist, Anders Bramah, who showed that if you could deliver non-uniform beams of radiation, you could deliver the radiation a lot better to the patient. But there was no way of delivering it at the time. So in about 1988, we came up with the idea of tomotherapy, which was to deliver these non-uniform beams in 360 degrees around the patient. And then we also came up with the idea, well, if we're going to be treating continuously around the patient, let's also have a CT scanner on board. So we really developed the first radiation therapy treatment system that incorporated a built-in CT scanner to verify that the patient was set up correctly. So we knew from the treatment plans, from just doing the calculations of the radiation dose, that we could avoid normal tissue structures close to the tumor much, much better than we could with conventional radiation therapy. So in other words, we could deliver sufficient dose to the tumor, but not damage normal critical structures really close to the tumor. Well, the University of Wisconsin is in Madison, Wisconsin. It has the largest and oldest medical physics program in the world. And so being a professor here allowed me to have great students and great colleagues. And really it was a team effort. And the place that was rich in medical physics knowledge and experience. And other people had started companies from the department before, so it was possible to do that. There was a path already plowed in the snow ahead. So the idea really started in 1988, and we worked on it for actually a few years, and then we got General Electric, in fact the French division of General Electric, which was headquartered in Bouc, France, to believe in the idea. So from 1994 to 1997, this was a French GE project at the University of Wisconsin. Unfortunately, General Electric decided to get out of the field of radiation therapy in 1997, and they sold the GE radiotherapy division, and so we started tomotherapy in 1997 following the sale of our previous company. In other words, we had the money to start it, and then started the company tomotherapy. So when we started, when we first had the machine running and we were starting tomotherapy for the first time, we wanted to use it on client dogs, in other words, people's pets who develop cancer. So large dogs often develop sinus tumors, and they were treated traditionally with cobalt radiation, and they would be treated with two beams, one beam from here and one beam from here. The animals would get rid of the sinus cancer, but they'd all go blind. So the first dogs that we treated with tomotherapy, we were able to treat the tumor, but they all remained sighted. So we went from 100% complication rate to a 0% complication with tomotherapy. So we knew that this was going to be very important for the field of radiation oncology. Yeah, so the first patients were palliative patients, so they weren't going to, they had very small chance of survival, and we were just treating a few of the large tumors that were causing them pain. So we were just using it for treatment of pain. But very quickly we started treating curative cases as well, and we found, as we had with the animals before them, that we could treat the tumor well and avoid complications from structures close to the tumor. So the system evolved in a number of ways over the years. Essentially, it looks pretty much like it did in the early days, but there are a lot of subtle improvements. Probably the most important one is that as you operate a machine, you find out the things that work well and don't work well. Find out the things that break and the things that don't break. And so basically, it's what we call in the United States whack-a-mole. You hit one thing and then you hit another thing and you hit another thing until you've solved the problem. So now the tomotherapy is one of the most reliable radiation therapy treatment systems in the world. It's now called RadExact. It's a new platform for tomotherapy, if you like. The other things are more subtle that you can't really see. One of them is that the jaws defining the field are much more flexible. It allows much faster treatments than it used to. One of the other things that we learned is that you can treat very long fields. So you can treat cranial-spinal fields. You could treat even total marrow or radiation with tomotherapy. We had never believed you could do that in the early days, and now it's being used routinely to give much better radiation therapy, especially for kids who have disease in their spinal column, and for patients that need to have radiation therapy in preparation for a bone marrow transplant. So a tomotherapy has a number of significant differences. The main one is it looks like a big CT scanner. And in fact, it has a CT scanner that's built into it, a fan beam CT scanner, which gives a very accurate description of how the patient's been set up. The other thing that tomotherapy is quite different is that it has an intensity modulation system that gives much greater degrees of modulation. In other words, you can deliver tens of thousands of small beamlets to a patient so that you can exquisitely increase the dose where you need it, where it's hitting the tumor and not hitting a normal tissue structure. And then very low radiation when it has to go through a normal tissue structure to get to the tumor. So one of the things that you have to deal with in radiation therapy is that the body's in continuous movement. So especially the lungs, the diaphragm is moving, and if the tumor is in the lung or the liver, which is just below the diaphragm, then the tumor can be moving as a function of time. And so what you can do then is, if you're imaging at the same time as the treatment, you can determine where the tumor is and then have the leaves adjust their treatment so that you're just hitting where you want to hit, and you're not hitting a normal tissue that doesn't need to be treated. In other words, the radiation is going instantly where you want it and not going instantly where you don't want it. I feel wonderful that the vision, if you like, in the original days is being manifest. And of course, it takes a long time to get the full vision of being able to treat tumors, avoid the normal tissue, guarantee that you're doing it because you're doing a CT scanner, and being able to then manage the motion as well. So it's great. It's wonderful to see the evolution in time. And things take a long time. That's really one of the lessons of invention and getting it to the bedside. So people have said for decades that radiation therapy won't be needed. As far back as my career, my whole career, people have said that drugs and immunotherapy are going to be the only way that people are treated. And radiation therapy is a wonderful treatment for local disease that can't be operated on effectively. So that's not going to change. It's very difficult to have the toxicity low enough for a drug to treat a very large tumor. Whereas radiation therapy can be delivered to a tumor, a dense, relatively large tumor, completely eradicate the tumor, and not have the violent side effects that you would require to treat with chemotherapy such a large tumor. So I don't see that changing in time. Radiation's a very effective way at managing tumors. And in fact, we've recently learned that the combination of immunotherapy and radiation can actually potentiate the immune therapy. And the reason for that is the radiation is actually waking up the immune system, sort of like delivering a vaccine that the immune system that says there's something wrong here, there's some damage here, let's go investigate and see what it is. So it's been shown then that adding both together in the right sequences can be very effective. My personal adventure with tomotherapy started in 2007, and we had just taken the company public, and in the fall of that year, in September, I was diagnosed with intermediate grade prostate cancer. So the prostate, my prostate had a fairly aggressive tumor. There was evidence of nodal involvement. So I needed to have the prostate treatment and the nodes surrounding it. So it was a relatively large radiation field. It really couldn't be managed well with conventional radiation therapy. So tomotherapy was, and would be still today, the perfect way to treat the nodal chains avoid the pelvic bones, avoid the rectum and the bladder, and still treat this complicated shaped field and the prostate. Well, that's more than 11 years out now. My PSA is very low, so I guess it worked. Yes, I in fact subjected the staff at the University of Wisconsin to my treatment planning abilities. I essentially took over one of the treatment stations for 2 days and tried all kinds of different ways to treat the field, and finally they agreed that I should stop. I'd found many very good plans, and so I was treated with my own plan. I also wanted to be treated in a slightly different way. Rather than going head first into the machine, I went backwards into the machine, which I think is the best way to treat prostate, instead of subjecting the patient having to go all the way into the machine. I was also treated on my stomach, so I was treated in the prone position, which allowed my generous intestinal system to be removed a little bit more from the field. So medical physics really is physics applied to medicine, and the most important areas are radiation oncology, radiology, and nuclear medicine, although we're also getting into other fields like surgery and pathology. So fields that involve imaging, medical physicists have long been experts in imaging. In fact, you know, astronomers are physicists too, and they're essentially imaging professionals as well. So we can contribute a lot from our education into the practice of medicine. Radiation oncologists are our partners in radiation oncology. I mean, they understand the biology of cancer. They understand the complications that can have and how patients should then be treated to help with the complications. So we're the technical experts, if you like, in radiation oncology, and the radiation oncologists are the biological experts and the clinical experts. And so combined then, we can form a team that can treat patients better and manage the complications and hopefully cure the cancer. So medical physicists are trained as physicists, so we're somewhat theoretical at times, somewhat mathematical, but we also work with engineers who are very specialized. So tomotherapy or Accuray employs electrical engineers, mechanical engineers, systems engineers, computer engineers. That's all the engineering skills that you really need to develop a very complicated machine. You can see that tomotherapy, it's a relatively complicated device, and all of those skills are really required. In terms of the computer engineering, even though you don't see it here, much of tomotherapy or other forms of radiation therapy now rely on relatively complicated large computer programs operating with very fast computers in order to calculate the radiation doses that are required to give a good plan for the radiation for the radiation oncologist to approve.